Today we're going to talk about the particle nature of light, or an experiment called the photoelectric effect. Real quick, just some bookkeeping here. We're going to find that joules are too big of an energy to use when we're talking about electrons and atoms. So we're going to define what's called the electron-volt. And this is the kinetic energy gained by an electron when accelerated through 1 volt of potential difference. And so if we do this in our SI units, kinetic energy, so the kinetic energy gained in this case would be the charge times the change in the electric potential, going back to 152 or 132. And so if we type in, this is the charge of that electron, 1.6 times 10 to the negative 19 coulombs, and then 1 volt, we get here 1.6 times 10 to the negative 19 joules. And so we just define that to equal 1 electron volt, and it'll just be much easier. Also, we're going to start using Planck's constant, and so here's Planck's constant here written by itself, and then in another form that we'll use occasionally, this h times c, which we'll talk a little bit more later, but it's another way to write it in terms of electron volts, which makes things a little bit easier. Now, the photoelectric effect is this effect that when you shine light on a metal, you can knock electrons out of the atoms. And basically what's happening here is the light is providing energy to overcome the Coulomb attraction of electrons to the nucleus. And here's a little cartoon. So the light shines down on the material. So this here in this little cartoon would be our metal. This is the metal right here. Light shines down and it knocks out electrons. So people noticed that this happened, and so they tried to study it to try to learn more about it. So our experiment, we defined just two pieces of metal. One's called the cathode, one's called the anode. And what we do is we do our experiment, we shine light on here, and electrons are released. Now, if the electrons are going fast enough, they'll actually reach the anode. And so if that happens, what we can do is, again, two experiments. The first one, we put an ammeter connecting the two pieces of metal. So an ammeter has a very low resistance. And so what happens is if an electron lands on the anode, all right, now what that does is it leaves behind sort of an excess positive charge in the cathode, and so this electron is really happy to come back through the ammeter and go back to where it left from, essentially. And so what this does is this gives us a measure of the number of electrons that land on the anode. This ammeter will give us the current, which tells us how many electrons are landing on the anode. Now, not every electron will reach the anode. They might get launched in different directions, etc. But this number is going to be proportional to the amount that are ejected. So connecting the ammeter here, we get a number that tells us proportional how many electrons are being emitted. Now, in the second version of this experiment, we connect the cathode and anode with a voltmeter. And a voltmeter has a very high resistance. And so this does not allow the electrons to travel back to the cathode once they hit the anode. And so what happens is they build up. And so you get a bunch of electrons on one side and a bunch of positives on the other side. And this is very similar to a capacitor. And you get to a point where there's so many you can sort of physically, there's so many electrons over here that these electrons cannot reach the anode anymore. They're repelled by those negative charges. And so you get to a point where the delta V remains constant, and that's the electric potential between the two plates. And it's basically measuring the electric potential between the between these two ends of this capacitor. Now what that tells us is this is proportional to the maximum kinetic energy of the electrons, because again, so the electrons are not making it to the other side. Now the potential energy difference between the two ends, the cathode and the anode here, is Q times delta V. Again, this is 132, 152 type stuff. And so the charge times this delta V, that gives us, that's the potential energy you have to overcome if you're launched from the cathode to hit the anode. And so since they're not making it, that means that the maximum kinetic energy would be this here. And so that's the kinetic energy where like the electron just barely gets right here, but then is deflected back. Okay, and so this gives us a measurement of the maximum kinetic energy. So the first experiment tells us how many electrons are being ejected, and this one tells us something about how much kinetic energy they have when they're ejected. So let's look at some of the things you can control in this experiment. So for a given metal serving as your cathode and anode, The two main things you control are the frequency and wavelength, which remember, for an electromagnetic wave, if we change one, we by definition are changing the other. And so you'll see different people talk about changing the frequency or the wavelength, but it's the same thing. The other thing is the intensity, and this is something that we learn in our first year physics, but I think sometimes we don't have the best grasp of it yet. And so this is the average energy transfer of the wave. Our actual units of this would be watts per meter squared, or power per area. And what that really means is the intensity is how much energy, the way I like to think about it, is how much energy are you supplying to some area per second. Now, the more intense it is, the stronger the electric field is. All right, so the intensity is proportional to the electric field squared. So we're going to compare the two different models. The first model is the model they used at the time, which is the wave model, and the second will be the particle model, which Einstein came up with. So in the wave model, as the electromagnetic wave falls on an atom, this oscillating electric field causes the electrons to oscillate, basically vibrate back and forth. And if you do this long enough, they should gain enough energy to jump out and be ejected. And so this energy they need is called, we call it eject for right now. And so the predictions of the wave model, so first, at high intensities, so if you're giving a lot of energy per that area per second, the rate of electron ejection should be proportional to the intensity of light. So if you add more energy per second per area, you should have more electrons coming out, which hopefully makes sense from this wave model. The other thing is at very low intensities, if you don't have very much energy coming to that area per time, there should be a delay before the first electrons are ejected. Some other predictions are perhaps there's a resonant frequency this electron has in the atom, and so maybe there are some resonant effects that could happen. Another thing the book talks about is this idea that people believed in this wave model that the more intense the wave was, the more kinetic energy the electrons leaving would have. And they describe this by saying it's like thinking about a 50-foot tsunami versus a 2-foot wave. The 50-foot tsunami is going to, in general, give more kinetic energy to this electron. Now, I think a lot of people can struggle with some of the math here talking about the wave model and intensity. And so I wanted to go through a problem here. So read through this problem and give this a try, and then we'll talk about it here in a second. And so what we're doing here is we say we have electromagnetic radiation with intensity of 0.3 watts per meter squared falling on an atom with a radius of 0.4 nanometers. How long will it take an electron to eject? And we'll say that assume each electron in this atom needs about 3 electron volts of energy to be ejected from the atom. So go ahead and pause this, give it a try, and then we'll talk about it. Okay, so when I did this, I got A here, about 3 seconds. So let's go through this real quick. And so the intensity, again, is watts per meter squared. So I write that over here as 0.3 watts per meter squared. So again, this is the power delivered to some area. So I want to multiply this by the cross-sectional area of the atom. And so that would be pi r squared. So pi, and then I'm going to write this as 0.4 times 10 to the negative 9 meters. And of course, I'll square this because that's the radius. So pi r squared. So this gives us the area, and also just unit conversion wise, these meters will cancel, and this will leave me with watts. All right, and so when I did this, I came out with 1.5 times 10 to the negative 19 watts, which of course is joules per second. Now, it's not exact, but this is pretty close, this number, to 1 electron volt. And so this is pretty close to 1 electron volt per second. And so what we're saying is the energy delivered to this atom is 1 electron volt per second. And so if we assume that all of that energy goes to 1 electron, all right, and 1 electron needs 3 electron volts to be ejected, then it's going to take about roughly 3 seconds for this to happen. So let's look at the experimental results. So the first experimental result is that at high intensities and at a fixed frequency, the rate of electron ejection is proportional to the intensity of the light. And that's actually good. So that agreed with the wave model, right? Intensity means you're sending more energy to that area per time, and if you do that, if you increase that, you get more electrons coming out. They agreed with that. Well, the second one, not so much. So electrons are ejected essentially immediately, so it's about 10 to the negative 8 seconds, independent of the intensity. So the wave model, how can the electrons pop out immediately, right? Even if you send a really low intensity wave, in the model it would have taken some time for the electron to jump out. Like the example we just did, it would have taken 3 seconds. Well, here, no matter what intensity wave you send, if electrons come out, they come out almost immediately. Another result that didn't jive well with the wave model is if the intensity is held constant, the number of electrons decreases with increasing frequency. Well, in the wave model, it's all about intensity. If the intensity is the same, then the energy you're delivering to that area per second is the same. And so why would you be getting less electrons? Now, it didn't stop there. Another result was if the frequency is below a certain value, which we call the cutoff frequency, no electrons are emitted regardless of intensity. So you could send a super intense wave, which means you're delivering a whole bunch of energy to that area per second, and you would still not get electrons coming out. And finally, if the frequency is held constant, the electron's kinetic energy maximum was independent of intensity. And so this is that example we were talking about, the wave model, comparing a 50-foot tsunami versus a regular 2-foot tall wave. And so in this experiment, if the frequency was held constant, the kinetic energy maximum didn't depend on intensity. So you could send a super big 50-foot wave and a 2-foot wave, the electrons would still come out with the same kinetic energy. And finally, the book will have little plots like this. So above this cutoff frequency, the electron's kinetic energy maximum is directly proportional to the frequency of the light with the same slope for all metals. So the wave model did not seem to be correct, and so we had to come up with, or scientists had to come up with a new model, and Einstein did just. Einstein's explanation is called the photon model, and he essentially proposed that light was quantized. And so it came in little packets, and these packets were later given the name photons. And so he framed 3 postulates about photons and their interaction with matter. So first, light at frequency f consists of discrete quanta, each of energy E equals to the Planck's constant times frequency, and each photon travels at the speed of light. The photons are emitted or absorbed in an all or nothing basis, and a substance can only emit or absorb an integer number of photons. And finally, a photon, when absorbed by a metal, delivers its entire energy to 1 electron. And so these 3 postulates explain all of the results of the photoelectric effect. So how do these postulates explain the experimental evidence? Well, the first postulate says that each photon has a certain energy. So for a given frequency or a given wavelength, your photon has a certain energy. And so that means if you want to turn up the intensity or turn down the intensity, whatever, you need to change the number of photons. So the more intense your light wave is, the more photons it has. So the more intensity means you're going to send more photons, which means you'll knock out more electrons. Furthermore, the electron is either knocked out or it isn't. So each photon has a certain amount of energy, and each electron, there's a certain cost to knocking it out. And so that photon can either knock it out or it doesn't. And this explains the 2 pieces of evidence, experimental evidence, that first of all, the electrons pop out immediately if they do pop out. So once those photons start coming, they're going to have enough energy to knock it out, or they're not. And it also explains why there's a cutoff frequency. So it's very unlikely for 2 photons to hit at the same time. And so basically, if you don't have enough energy in that photon, you're never going to knock out an electron. Another very curious thing that this model explains is one of our experimental results that said the number of electrons ejected decreases with increasing frequency. So this is really weird. Now, one thing I should be real clear about is that this is if the intensity is held constant. Okay, so in this experiment, you can hold the intensity constant and adjust only the frequency. Well, what happens is, if you look over here at this equation, if the frequency increases, that means the energy of each photon increases. Well, if the intensity is held constant, intensity is the energy that's delivered to that area per time. And so if the intensity is held constant and each photon has more energy, the number of photons will decrease. Thus, the number of electrons that's ejected will decrease. Einstein summarized a lot of what he did here in this nice little equation that says the kinetic energy equals Planck's constant times the frequency minus the work function. So what this really is just conservation of energy. This h times f is the energy of the photon, and this w, the work function, is the energy cost for the electron. So what this says is if you take the energy of the photon and subtract out the work function, you get the maximum kinetic energy. This should say maximum. Of your electrons. You just basically subtract those two, and that's what's left over. And this explains the last two experimental results. First of all, that the kinetic energy max is independent of the intensity, that whole 50-foot wave versus 2-foot wave. Well, nowhere in this equation is the intensity. And finally, if you look at this, this is basically the equation of a straight line, right? If you write this equation out as sort of a y equals mx plus b sort of thing, where f is your x, then the slope is Planck's constant. And you get those graphs that we were showing before of the kinetic energy versus frequency. They look like this. It's like a nice linear line. All right, so we'll talk more about this.